for the introduction. It's a pleasure to be here, and I thank the organizers for inviting me. So as Doug mentioned, I come from, well, I guess there's sort of three communities here. There are a number of people here who work on geometric numerical integration, structure-preserving time integrators. And then there's a number of people who work on structure-preserving spatial discretization. And finally, of course, there are specialists in numerical relativity. My hope is that this talk will tie together some things from all three of those. I have the least to say about numerical relativity, but I do have some thoughts on how maybe understanding a bit about structure-preserving time discretization and its relationship to spatial discretization might provide some lessons or hopefully start a good conversation that we can learn from one another. Let me just first acknowledge the support of the NSF. Okay, so let me start by just sort of setting the stage for how we talk about structure-preserving integration, or just integration of ODEs generally. All right, so suppose we have a first-order initial value problem. So I'm looking for some curve y of t that satisfies this system of equations. So here f is a vector field with certain initial conditions. Now, I'm typically going to be thinking of y in sort of classical systems of ODEs. We think of y as living in d-dimensional Euclidean space, but it could also live in some function space, possibly even infinite dimensional, or it could be on a manifold. But for now, you can think of everything as being in RD. So if I look at, suppose we have existence and uniqueness of solutions for various initial conditions. This defines a time t flow map that basically sort of fast forwards our solutions by time t. And this tells us about the solutions of this differential equation. Okay, so obviously for many systems, especially nonlinear systems, we can't solve them exactly, so we need numerical methods. And a numerical integrator, specifically I'm going to be looking at one-step numerical integrators. One-step numerical integrator basically approximates this flow map by something that I'm going to write as capital phi sub h, where h is the time step size. All right, so this approximately advances the system by time h, and by advancing time step by time step recursively, we can get an approximate solution, which is a sequence of points y sub n. All right, so this is basically a very generic description of dynamical systems and the kinds of methods we might want to design to simulate them. However, of course, physical dynamics, the kind we see in physical systems, are highly non-generic. They often have way more structure than this. Some of the structures that we're commonly concerned with in geometric numerical integration, structure-preserving numerical integration, are Hamiltonian symplectic structure. Our solutions might be defined by some variational principle. We may also have some symmetries, and using Noether's theorem, those might result in conservation laws, things that are conserved by the flow. And because these dynamics are non-generic, these flows are going to have some special structure. And the goal of geometric numerical integration is to design numerical integrators so that these approximate flow maps have some or all of the properties, or as much as possible, of the exact flow map. All right, obviously, we can't preserve everything without getting the exact solution, but many of these properties we can, in fact, preserve exactly. Or at the very least, sometimes we can't preserve things exactly, but we can preserve them within some bounded error that doesn't grow over time. So let me just give a quick tour of what some of these generic one-step methods look like. One of the oldest is Euler's method, which is written here. This is an explicit method, right, because I actually have a formula for yn plus 1 in terms of yn. And it has order 1, meaning that if I integrate over a fixed time interval, my error is going to be O of h to the 1. There's the backward Euler method, which is basically on the right-hand side here. I evaluate f at yn plus 1. This is an implicit method because I actually have to solve this nonlinear system using Newton's method or something like that every time I take a time step. And it's also order 1, so why would I go through that extra expense? Well, backward Euler has some desirable stability properties. So people often use backward Euler and things like it for systems with sort of very strong damping or other stiff features. There's the midpoint method, which is also an implicit method, and it's order 2, in fact. So here we evaluate f at the midpoint of yn and yn plus 1. So this is an implicit method. How can we get higher order explicit methods? Well, Runge came up with one of the classic methods, the explicit midpoint method, which is also sometimes just called the midpoint method. And it's very much like the midpoint method, except instead of actually evaluating f at this midpoint, we approximate the midpoint by taking a half step of Euler's method. So here we get order 2. It's explicit because I don't have any n plus 1s on the right-hand side, but there's a bit of an additional cost because I actually have to evaluate f twice at every step. So that sort of doubles the cost per step. One of the workhorses of scientific computing is the classical fourth order Runge-Kutta method, sometimes just called RK4. And we basically here evaluate f at 4 different points, approximating sort of the endpoints and the midpoint. And then we combine them using this thing at the end. We basically combine the f's evaluated at those 4 different points. And in general, the general form of a Runge-Kutta method with s stages is we basically define these stages k sub I, which are approximately f evaluated at some point, which is determined from the previous step yn, and these coefficients aij, and the other stages kj. Right? And then after we've computed all the stages, we compute yn plus 1 using this formula. All right, so these can be either explicit or implicit. They're explicit precisely when the stages ki only depend on the previous kj. And the order theory for these was really actually developed quite recently in the 1960s and 70s by John Butcher, with important contributions by Ernst Heyer and Gerhard Wahner. Okay, so why isn't this the end of the story? Why can't we just say, all right, we can look at the implicitness, we can look at implicit or explicit, we can look at the order, we might want to look at stability. What else is there to look at? Well, let me show just a couple of examples. Very simple mechanical system. Let's look at just the ordinary pendulum. So on the left-hand side, I'm going to integrate the pendulum using Euler's method. On the right-hand side, I'm going to integrate using a method called symplectic Euler, which is also explicit in order 1. So these cost exactly the same to compute. Right, so in spite of the fact that these are both explicit first-order methods, you see as we integrate for some time that they actually behave quite differently. Right? So we're getting some very non-physical behavior from Euler's method. Effectively, what Euler's method is doing is artificially injecting energy into this system. Right? Whereas the symplectic Euler method, basically qualitatively, we're seeing it behave the way one would expect a pendulum to behave. So that's sort of a first order example. And just to give another example, here's RK4 used to simulate the outer solar system. I think this was for something like 250,000 years with a long time step. And you see, I think at some point, what is that? I think that might be Jupiter gets ejected from the solar system. So you have some strange things happening, and that's due, in fact, to you have a dissipation of energy, and you don't have conservation of linear or angular momentum by RK4. Whereas if we apply something called the Sturmer-Verlet method, which is a symplectic method, these are large time steps, so you see some precessions here in the orbit, but we don't see anything like anything getting sucked into the middle or shot out of the solar system. So this is sort of some motivation for why there might be features of these methods that allow us to, accurately simulate physical systems, conservative physical systems, due to properties that go just beyond their order of accuracy or their truncation error. Okay, so why am I talking about this at a numerical relativity workshop? Well, a lot of the things that the methods that we use for simulating ODEs are also used for simulating time evolution PDEs. And how do we do that? Well, if we have a time evolution PDE, we can semi-discretize it in space. So basically replace our infinite dimensional function space by a finite dimensional one, maybe using a finite element method or a finite difference or volume method, right? And that gives us, turns this time evolution PDE into a finite dimensional system of ODEs, right? And then we generally apply some numerical integrator to advance this finite dimensional system of ODEs in time, and that gives us an approximation to our time evolution PDE. Right? And of course, if the PDE has some Hamiltonian or other structure, it makes sense to discretize in time using a geometric numerical integrator. Basically, we don't want our simulation to look like the bad pendulum on the left there, or the solar system where planets get ejected. We want to take care to see if we can preserve these structures. Yes?
Yeah, thank you. From time to time in numerical relativity or in astrophysics, we engage in discussing the benefits of trying to go in this direction. So obviously, when you show the pendulum,
Mm-hmm.
that was a complete wrong solution. And
Yes.
the same with the Jupiter disappearing.
Yeah.
So what's a good estimate of the error of the other solution, the one you're iterating with a symplectic iterator, with one of these energy preserving? Because the system has many more degrees of freedom, and you're preserving a combination of all of those, and that means one answer. But the system could have wildly large errors, even though the structure of the orbits are reasonable.
Yeah. No. So as I mentioned, you certainly cannot preserve everything. These things are going to be involve errors. There are some results for geometric integrators that actually show that you get a slower growth of global error over time. So in many respects, not just with respect to looking at invariance or things like that. If you actually look at the global error, you can see that there's a fair amount of cancellation with some of these methods. I'm not going to be able to get too deep into that, but one can look at traditional error metrics and actually see some benefits from using these methods.
So let me make a comment. So the symplectic order, as Ari said, is only a first-order method, and therefore very inaccurate. However, the theory is there to develop symplectic methods of arbitrarily high order. That's one of the things that we're studying. And arbitrarily high order methods become very accurate. Right, but then you can use arbitrarily high order methods that are not symplectic. So that's what I'm trying to say. What rigorous result?
Well, then the question is like a rigorous result.
If you have an integrable system,
And you integrate it over a very long time, then in the non-symplectic method, the error will accumulate like the step size to the power times the square of the length of the input. With the symplectic method, it's step size to the same power times the length of the input. We are winning essentially square root of the length.
Okay. All right, great. But yeah, no, these are important things to ask. It is worth asking, what does this buy you, aside from, like, obviously if it's a symplectic integrator, preserves the symplectic form, but what else do you get? And that's one of the things that you do get. All right, so one thing to note, though, is that there's that semi-discretization step. So if your original PDE has some Hamiltonian structure, you want to make sure that the semi-discretization also preserves that structure. And looking at which spatial discretizations preserve these kinds of structure can guide what sort of spatial discretization methods we might want to use. And one example that I'm going to look a little bit at later is the preservation of divergence constraints in Maxwell's equations. So Maxwell's equations, like Einstein's equations, have some evolution equations, but there are also constraints that are automatically preserved by the exact evolution. Turns out this is related via Noether's theorem to gauge symmetry, and we can preserve this gauge symmetry if we semi-discretize using Nedelec edge elements. And looking at sort of the preservation of some of these structures in computational electromagnetics led to the development of various techniques, including finite element exterior calculus, for really describing why these things have the spatial structure preserving properties that they do. So a big question that I absolutely don't know the answer to is, and this is sort of one of my motivations for talking about this, has to do with the constraints in general relativity. Could it be that an appropriate choice of discretization in space might lead to automatic preservation of the constraints in relativity, or perhaps within some error that doesn't grow over time, without having to do imposition of the constraints using damping or Lagrange multipliers or some other techniques? I think that's an important question to explore, and that's sort of one of my motivations for talking about this. Okay, so here's the outline of my talk. I'm going to talk a little bit about geometric numerical integrators for Hamiltonian ODEs, going into more detail of what I showed you in that movie. And I'm going to briefly talk about how we can apply this to do time stepping for semi-discretized PDEs with the example of the wave equation. And after that brief interlude, I'm going to look at Maxwell's equations and gauge symmetry and these divergence constraints and how they can sort of guide our choice of spatial discretization. And finally, I'm going to talk at the end about some recent work involving local Hamiltonian structure, not in time but in space. Basically, how can we ensure that all that stuff that was going wrong with the pendulum when we discretized in time, what's the analog of that in space? And it results in something that we call a multi-symplectic conservation law, and I'll talk a little bit about how we can preserve that when doing spatial discretization. Okay, so first, Hamiltonian ODEs and geometric integrators. So I'll start with a very simple Newton's second law type of second order ODE, F equals ma. So on the left we have some mass matrix times acceleration. On the right-hand side, we have a conservative force, which is minus the gradient of a potential energy function V. All right, and there are many ways of writing this as a first-order system, but one of the best is to define the conjugate momentum, P, which is just mass times velocity, and we can now write the equations in this first-order form in terms of Q and its conjugate momentum. And we can also define this function called the Hamiltonian, which I've written here. This is basically kinetic energy. So this ends up, if we substitute, we can see that this is the same as sort of 1/2 mv squared. So kinetic energy plus potential energy. So the Hamiltonian in this case is the total energy of the system. And it turns out that this first order system has the following form. Q dot equals partial h partial p, p dot equals minus partial h partial q. And systems having this form are called canonical Hamiltonian systems. The canonical is important. There are other types of Hamiltonian systems that have different types of structures or different Poisson brackets and things like that. And I'm specifically here looking at the canonical structure on R2D. And these can be defined for any function h, not just the kinetic plus potential Hamiltonian. All right, so what are some of the conservative properties of Hamiltonian systems? Well, first of all, one of the best known is energy conservation. So since our Hamiltonian here doesn't depend on time, you can take d by dt of h, apply the chain rule and these equations, and immediately see that energy is an invariant of this system. A a bit more subtle, but actually extremely important, is that the flow preserves this differential 2 form, which here we're in a vector space, so it's just a bilinear form, called the canonical symplectic 2 form. So this I'm writing as little omega. It's dqi wedge dpi, where here, well, a lot of relativity people here, so I don't have to say too much about the Einstein index notation, where I'm assuming a sum over I here. And another way of seeing what it means to, for the flow to preserve this, specifically what this means is that the Jacobian is a symplectic matrix, in the sense that if I conjugate this matrix J, which corresponds to this bilinear form, if I conjugate it by the Jacobian, right, I get back J itself. So J is preserved by this flow. Right. An immediate corollary of this is that the flow of a Hamiltonian system preserves volume in phase space. Right? And this is a result known as Liouville's theorem that follows immediately from the symplecticity of the flow. So this is nice to know, especially if you're interested in looking at statistical properties or whatever of a Hamiltonian system. The fact that there's an invariant volume form is important. And one of the most fundamental results in geometric mechanics is Noether's theorem, which says that there's a correspondence between symmetries of a mechanical system and invariant momentum maps. So for example, a system with translational symmetry, you get conservation of linear momentum, right? And a system with rotational symmetry, you have conservation of angular momentum. Right? So for example, if I'm looking at an n-body problem, say like the outer solar system I had there, the fact that the Hamiltonian really only depends on the distances between the bodies, and not, it means that I can just rotate everything, and I also get a solution to the same equations. So that's basically, Noether's theorem says that because I can rotate this system and it's unchanged, that's why I have the law of conservation of angular momentum. Right? And typically these invariants sort of have the following kind of quadratic form. So for conservation of linear momentum, I won't have this matrix A. I'll just have some conjugate momentum dotted with some vector. Angular momentum, on the other hand, is a quadratic invariant. All right, so what are symplectic integrators? Symplectic integrators are one-step methods where this approximate flow, right, the flow of the numerical method, also preserves the symplectic form whenever applied to a canonical Hamiltonian system. Right, so if I apply the method to a Hamiltonian system, I have this property of the Jacobian of the flow map being symplectic. So Runge-Kutta methods actually can be symplectic. And one of the I think, tidiest characterizations of symplectic Runge-Kutta methods, which was discovered by Botchev and Scoville, is that a Runge-Kutta method is symplectic if it conserves quadratic invariance. Right? So in particular, these methods preserve the symplectic form, and you also get conservation of those linear and quadratic momentum maps that we saw on the previous slide. So a symplectic Runge-Kutta method will also preserve, for example, linear and angular momentum if that's a property of the system it's simulating. So what's the third thing? So I mentioned symplecticity, momentum conservation, but then there's energy. There's the conservation of the Hamiltonian itself. So it turns out that symplectic Runge-Kutta methods do not preserve the Hamiltonian exactly. However, they do something which is almost as good. You can show using backward error analysis that they preserve a nearby modified Hamiltonian. So that means that there's no energy drift as long as we take a fixed time step size h. Just a quick caution, something that often trips people up about symplectic integrators, is that you have to be careful about using adaptive step size control. Right? So if you just use a typical adaptive time step selection routine combined with a symplectic integrator, what you're effectively doing is changing the modified Hamiltonian every time you change the time step. So it's been observed that you can, in fact, get drift in the Hamiltonian if you sort of blindly apply adaptive time stepping. And there's been some more, quite a bit of work about how to do that a little more carefully so this doesn't happen. One of the things I've heard sometimes is sometimes people say that if you use adaptive time stepping with a symplectic integrator, it's no longer symplectic. Now that's not true. Composition of symplectic maps is always symplectic. So these methods are still symplectic and they're still momentum preserving, but you lose this nice property of nearly preserving the Hamiltonian. Yes?
In your earlier rubric with the solar system, the wobbling of Mercury was presumably this H tilde, right? Is that a symplectic?
So that was just the outer solar system. So I think that was Jupiter. Yeah, but yeah, I mean these were actually fairly large time steps. So
that wasn't an H twiddle that was making the stable wobbling of that. I'm just looking.
Yeah, this was artificial wobbling. This was not.
That was artificial. So okay.
Yeah, no. So this is the sort of thing. So I mean, if you imagine something simple like a harmonic oscillator, right? If I'm not making large errors in the energy, I'm going to have to be making those errors in the phase. So you do see some precession and things like that happen artificially if you even for simple things like just a two-body problem, you'll see things like that. So in some sense the error is a little bit like whack-a-mole, where if you're having smaller errors and if you whack down the error in one area it's going to pop up in another, and here you see it there. However, it's not a zero-sum thing, as I mentioned, and as Ari mentioned, you do get slower growth of the global error. Okay. So actually, this is about as good as we can expect. There's a theorem of Ge and Marsden that says that it's impossible for a fixed time step symplectic method to be energy and momentum preserving. So having it be exactly symplectic, exactly momentum preserving, and basically energy preserving within some bounds is about the best we can hope for. There are also other methods where people look at what are called conjugate symplectic methods, which are not exactly symplectic, but they nearly preserve a symplectic form. And those include things like the trapezoid method. All right, so what Runge-Kutta methods are symplectic? Well, of the ones I wrote down before, the midpoint method is symplectic. And the midpoint method is, but here I mean the implicit midpoint method. The explicit midpoint method is actually not symplectic. But the implicit midpoint method is, and it's actually the lowest order example of a family of methods called Gauss collocation methods, where basically, so the midpoint is the sort of the lowest order Gauss quadrature, and if you take sort of higher order Gauss quadrature nodes, you can construct these things called Gauss collocation methods that are also higher order implicit methods. What methods aren't symplectic? Well, it turns out that no explicit Runge-Kutta method is symplectic. So this would seem to tell us that if we want symplecticity, we have to give up using explicit methods, at least as long as we're in the world of Runge-Kutta methods. All right, so to find explicit symplectic integrators, that means we need to go beyond Runge-Kutta methods. So let me give you show a couple of examples of explicit symplectic integrators. So one is this method called the symplectic Euler method. All right, so this is an order 1 method. So this looks a lot like Euler's method. So the first line is actually exactly the same as Euler's method. Right? I'm just advancing Pn using the force evaluated at Qn. But then when I advance Q, I actually, rather than using Pn, I use the Pn plus 1 that I just computed. Right? So I don't treat both lines the same. I kind of use the Euler method for the first line, but something that looks like the backward Euler method for the second line, And even though it's backward Euler for the second line, in this case, it only involves something I've already computed, so it's explicit. And there's an order 2 method called the Sturmer-Verlet method, which is sort of a symmetrized version of this. What I do is, rather than advancing p by a step and then q by a step, I advance p by half a step to get an approximation of p at the midpoint. Then I advance q by a full step using that midpoint approximation to p that I just computed. And then I advance p again using that new q that I just computed. Right? And in a way, this is sort of like using the trapezoid method on the first and last lines and the midpoint method for the second line. So this is kind of like a combination of Euler and backward Euler. This is like a combination of trapezoid and midpoint. And these are examples of what are called partitioned Runge-Kutta methods. So a partitioned Runge-Kutta method basically is sort of like using a different Runge-Kutta method for the q part and the p part. And now it turns out partitioned Runge-Kutta, so these are examples of explicit symplectic partitioned Runge-Kutta methods for this type of system. They don't preserve all quadratic invariants, so they don't preserve things that have, say, like q squared in them. But they do preserve those QP terms, which are actually all that we need for symplecticity and momentum preservation. So for both of these methods, we can actually eliminate, another way of looking at this, we can eliminate the p variables. And both of these methods can be written as this sort of second order centered finite difference method in Q, which you can see as being sort of an approximation of the original second order form of the Newtonian equation. Okay, so there's another family of methods that we can sort of, that are a natural generalization of symplectic Euler and Sturmer-Verlet. So suppose we have a Hamiltonian, H, that we can write as the sum of two other Hamiltonians. And suppose that I don't know how to integrate this Hamiltonian system with H exactly, but I do know how to integrate each of these subsystems exactly. Right, so the idea of a splitting method is I approximate the flow corresponding to H by alternating back and forth between the flows for H1 and H2, which I actually can compute. Right, so since this is a composition of Hamiltonian flows, it's symplectic. And one example is actually what we've already seen. If we split the Hamiltonian into the kinetic part and the potential part, right, so this is the Hamiltonian system corresponding to just H1, and this is the system corresponding to just H2, right? And we can actually integrate these exactly, because for this one on the left, P is constant, right? So I'm basically just integrating a constant vector field for Q. And likewise, over here, Q is constant, so I can integrate this exactly. And the symplectic Euler method is something called the Lie-Trotter splitting for this, which is basically I do a step of the second system and then a step of the first system. Sturmer-Verlet corresponds to something called the strength splitting, which is I do half a step of this one, then a full step of this one, then half a step of this one again. Right? And you can actually get higher order explicit methods by alternating repeatedly back and forth with if I just alternate back and forth with half time steps, I just get multiple steps of Sturmer-Verlet. But if I choose if I carefully choose different time steps and compose them, you can actually find that you can get higher order explicit methods, and sometimes these steps in fact go backwards in time. So there was some early work in the 1990s on this by Yoshida, Suzuki, Robert McLaughlin, and a lot of work by many people in this room, which is why I didn't list any more names, because I didn't want to forget anybody. But there's so I think it's safe to say that this was some of the pioneering work in that area, and a lot has been done in the meantime. Right? And one of the nice things about the splitting methodology is you can use it for things other than Hamiltonian systems. So if I have a system that might not be Hamiltonian, but maybe it's volume preserving, maybe I have a divergence-free vector field, right? If I can write that as the sum of divergence-free vector fields and integrate each of those exactly, right, then the composition of those is also going to be volume preserving, right? And you can do this for systems that preserve foliations. You can also do it for methods on manifolds, not just in Euclidean space. And there's a large literature out there on splitting methods. So that's basically what I want to say about these methods for ODEs, and we've seen some applications of how they can be applied in mechanics. Let me just give a very simple example of how you could use one of these methods to integrate a PDE. All right, so let's consider sort of a very simple example. You can do more complicated examples than this. I could have done a semi-linear wave equation or sine Gordon or something like that. But let's just look at the wave equation, which I'm writing as u double dot equals Laplace u on some domain omega. And I'm going to put 0 Dirichlet boundary conditions on the boundary of omega. All right, and we can view our function u, we can either view it as a function of t and x, or we can, as I'm going to prefer to do it here, view it as a curve in the Sobolev space H1, 0. And here, H1 is the space of L2 functions with L2 partial derivatives. And this ring on the top means that that u vanishes on the boundary in the trace sense. All right, so I can write this in the following weak form. I can basically, here these angle brackets represent the L2 inner product. All right, so if I rearrange this, take the inner product with a test function v, and I integrate by parts for in space, I get this sort of weaker variational form of the problem where v is an arbitrary test function in H1, 0. All right, so now suppose I take a d-dimensional subspace, which I'm going to write as v sub h. Right, so this could be, for example, a finite element subspace, or it could come from a spectral method or something like that. Now I'm going to be looking for a curve in my finite dimensional function space VH such that this weak problem is satisfied, but only for test functions that are also in that space VH. Right, so I'm looking for solutions in a finite dimensional space with test functions in that same space. Right, and if I write this in a basis, what I get is a square system of the following form. I can basically, in a basis, this L2 inner product becomes a mass matrix M. This grad UH, grad VH, this bilinear form is represented by the stiffness matrix K, right? And I get a system in this form. So this is actually a finite dimensional Newtonian system, and therefore it's Hamiltonian, just like we saw before. And here the mass matrix is precisely the mass matrix for this method. And the potential energy I can write as this quadratic form, basically treating the stiffness matrix as a quadratic form here. All right, so once I've written the system like this, I can apply any of the previous methods. And as you can imagine, if you apply a symplectic method, you could use Sturmer-Verlet or something like that, we're going to get preservation of the symplectic structure for this problem, and we're going to get near energy conservation. If I were to apply something like RK4 or backward Euler or something like that, I would not have those properties. All right, so this can also be extended to semi-discretization of the wave equation by mixed finite element methods like Rabi-Artoma or BDM, as well as semi-discretization using what are called hybridizable discontinuous Galerkin methods. There's a nice paper on the wave equation specifically by Sanchez et al. And I also have a paper with Robert McLaughlin talking about sort of semi-discretization of these types of problems that I'm going to say more about a little bit later. Okay, so that was sort of the brief interlude illustrating sort of for a simple type of problem how we can use semi-discretization combined with geometric integrators to evolve certain types of time evolution PDEs. So now I'm going to look specifically at Maxwell's equations. And as I mentioned, one of the reasons I'm interested in Maxwell's equations is they have both evolution equations and constraints. Right, so my unknowns here, I basically have 6 unknowns, which are the sort of components of the electric and magnetic field, sort of 6 independent unknowns, I guess. But I have 8 equations here, right? I have 2 vector equations, and then these 2 constraint equations, div b equals 0 and div d equals rho. Now these constraints are automatically preserved by the evolution equations, which you can see just by taking divergence of both of the evolution equations. So if the constraints are satisfied by the initial conditions, right, at the initial time, then they remain satisfied for all time. So really, you only have to worry about the constraints for the initial conditions, and after that, it's automatically taken care of by the evolution. However, that's true only for the exact evolution, and it's no longer true once you semi-discretize Maxwell's equations. And there are many ways of semi-discretizing Maxwell's equations. Some of them will sort of use E and H as the primary fields, and there are various ways of trying to impose these constraints, including using Lagrange multipliers. One way we can understand where the constraints come from, though, and get an idea of one good way to discretize these equations is by writing Maxwell's equations in terms of the vector potential and scalar potential. And here, I'm going to have the vector potential be a vector field, which I'm going to assume is an H curl with a vanishing tangential component. That means it's an L2 vector field, and its curl is also L2. Right? And H1 is the Sobolev space I mentioned before. And given the vector potential and scalar potential, I can define the electric and magnetic field in this way. All right. So if I define E and B in this way, I automatically get that this first line is satisfied strongly. Right? So here I just, I get B dot equals minus curl E by taking the time derivative of B equals curl A. Right? And I get div B equals 0 by the fact that divergence of a curl is 0. Right? What about this second line involving the evolution of the electric flux density D and its divergence constraint? Well, I can write that in the following variational form. Right? Again, I'm basically taking here the dot product with a test function and integrating by parts in space. Right, so this is the weak form of d dot plus j equals curl h, and this is the weak form of div d equals rho. And another way you can see, just from this variational form, that the constraint is preserved by the evolution is that if I take, so here my a prime is going to be my test function, right, corresponding to the vector potential. So if I take a prime to be the gradient of some scalar test function phi prime, right, then I get precisely that the time derivative of the second line is equal to 0, meaning that if the second line is satisfied at the initial time, then it's going to be satisfied for all time. Right? And this is actually a special case of Noether's theorem corresponding to the gauge symmetry, where I can basically add any gradient to the vector potential and it doesn't change the solutions, right? Because if I add, right, if I do this here, I'm assuming that phi prime is constant in time, E doesn't change and B doesn't change because curl of a gradient is 0. All right, so since I had some gauge symmetry there, I can actually choose what's called temporal gauge, right? I'm just going to set my scalar potential to 0, and I just get this equation in terms of the vector potential, which is basically the curl wave equation, as it's sometimes called, where I've got sort of a source term corresponding to the current. Now in the 1980s, Nedelec introduced 2 families of edge elements for constructing sort of finite element approximations of H curl. Right? He also constructed some closely related families of face elements for another space, H div. But in this case, we've written everything in terms of H curl function. So if I use, if I restrict to the Nedelec finite element spaces for my A and for my A prime, I get the following sort of Galerkin method, which was introduced by Nedelec in sort of his original, I think, 1980 paper. Right, and in a basis, right, this again is going to take the following Newtonian form. Right? So again, once I semi-discretize Maxwell's equations, I have something that I can now apply, right, that has this Newtonian or Hamiltonian structure, and I can apply a geometric integrator to it. So one thing to note is that although since the divergence of a curl is 0, right, div BH equals 0 automatically holds. However, the charge conservation constraint div D equals rho here is only going to hold in a much weaker sense, right, in the sense that it holds not for arbitrary test functions, but for test functions that are the gradient of some, basically something in a finite element space of scalar functions. So in this case, it'll be a Lagrange finite element space of some degree, so that the gradient of functions in this space are admissible test functions here. All right. So there are a few important things here to realize. So first of all, we had that symmetry, that gauge symmetry that resulted in preservation of the constraint. However, it was essential when we did the semi-discretization that we preserve the fact that divergence of curl is 0 and that curl of gradient is 0. Otherwise, the constraints will generally be violated. Right? And looking at what finite element spaces are compatible with these sort of this complex of differential operators, gradient, curl, and divergence, led to the development of finite element exterior calculus to really sort of explain how these things are constructed and what some of their numerical properties are. So I'm briefly going to mention some recent work that's in a preprint with my former postdoc, Yasha Berchenko-Kogan, who's now at Hawaii, on sort of doing domain decomposition and hybrid methods for Maxwell's equations to try to get a little bit of a stronger statement about conservation, about charge conservation in Nedelec's method. So given a triangulation of the domain, I'm going to define the broken H1 and H curl spaces as follows. These are basically the spaces of functions and vector fields that are not necessarily in H1 or H curl on the entire domain, but only on each triangle, and they can be discontinuous between different elements. So these are sort of discontinuous H1 and discontinuous or piecewise H curl. All right, and I can actually define a slightly domain decomposed variational principle for Maxwell's equations where I allow A to be in these broken spaces, and I enforce sort of continuity and boundary conditions between elements and at the boundary using Lagrange multipliers, which I'm going to call H hat and D hat. Right, so when I integrate by parts over something that only has support on K, I end up with this boundary term, which involves this H hat and D hat, and I get these last two lines basically enforce the continuity and boundary conditions. Just as before, we can use gauge symmetry to set the scalar potential to 0 and eliminate the equations involving the scalar potential. Right, and this gives us an evolution for the vector potential, which is in that broken space, but it also gives us an approximation for the trace of H, which is in H curl. Right? And then the D hat can be recovered by just solving this ODE. Right? And it follows that we actually get, right, via this domain decomposed variational formulation, we can see charge conservation arising in that way. Right? We can take finite element subspaces, apply to that formulation, and get this hybrid method. So now, rather than just evolving AH, we're evolving AH and this approximation, this curl-conforming approximation to the magnetic field. And then we can recover a div-conforming approximation to the electric flux density. And one example of this is we can hybridize Nedelec's method. Right? So we can take discontinuous Nedelec elements and, well, if we want to, this is something that's not exactly computable, but if we want to exactly enforce the continuity conditions, we could take this VH1 hat to be all of H curl. In practice, it suffices to take a sufficiently large Nedelec space to enforce these continuity and boundary conditions. All right, so if we take this hybrid approach, it's a theorem of Verchenko, Kogan, and myself, that if the initial conditions satisfy these constraints, then they hold for all time. And in fact, if the initial condition satisfies the charge conservation constraint in the Galerkin sense, then we can find an initial condition for this electric flux density d hat such that div d hat is equal to rho strongly. All right, so what this tells you is that given a solution to Nedelec's method, right, there's a corresponding solution of the hybrid Nedelec method with strongly charge conserving d hat. And just a remark that computing h hat and d hat can be seen as an optional post-processing step. In fact, right, this AH is just a solution to the standard Nedelec's method. So I think the main value of this result, 5 minutes, okay, is that it says that, whereas it appears that Nedelec's method only conserves charge in this much weaker Galerkin sense, you can show that every solution is actually shadowed by some d hat, which you can either compute or not, depending on whether you want to. It's actually shadowed by an exactly strongly charge conserving electric flux. Here are just some numerical experiments. These are actually the exact same solutions, except here I've computed the divergence of dH, and here I've computed the divergence of dH hat, and you can see that they're exactly charge conserving. All right, so we get some drift in charge, sort of if I look element by element with Nedelec's method, but it's actually, this is sort of an illusory thing. If you look at the sort of d hat that shadows it, you can see that it's exactly conservative. And here's just sort of comparing a couple of solutions in the frequency domain, where basically the d and d hat look exactly the same. But you can see this one has sort of some spurious charges, and this one is exactly divergence free. We've got have some superconvergence results as well of this approximation h hat to the magnetic field. All right, so finally, and this is just going to take a couple minutes, I just want to briefly, I guess, gloss over some work with Robert McLaughlin on Hamiltonian structure in space. So what is the analog of Hamiltonian structure for sort of PDEs in space, even PDEs that are not time dependent? All right, so there's this generalization where sort of my UIs are playing the role of QIs, and instead of just a single, instead of having conjugate momenta PI, I actually have this whole matrix of conjugate momenta. Basically, I have sort of a conjugate momentum for each spatial direction. Right? We have these equations called the de Donder-Weil equations, which are a generalization of Hamilton's equations of mechanics. They satisfy instead of just a single canonical 2 form, we have a collection of canonical 2 forms, omega mu. And these satisfy the multi-symplectic conservation law, which say, so in time, it says that the canonical 2 form has 0 time derivative. Here, this says that it has 0 divergence. Right? I can also write this in an integral form by integrating over some subdomain and applying the divergence theorem. So I can write the multi-symplectic conservation law in this integral form. And in fact, right, so the m equals 1 case just corresponds to Hamiltonian systems of ODEs. Right? And if I think of k as being an interval in time, what this is saying is that the difference between the symplectic form at the left and right endpoints is 0. Right? And this is generalizing it to the case where I've got some some domain in space or space-time, and I say the integral over the boundary is 0. So one example is we can write sort of semi-linear elliptic PDEs in this form, including Poisson's equation. So this is the Hamiltonian. You can also get hyperbolic PDEs by changing the signature of this tensor A. And what does this multi-symplectic conservation law really say? Well, it says something about a symmetry between sort of perturbations to the u's and perturbations to the sigmas. This is related to reciprocity laws in physical systems, including elasticity and electrostatics. It's related to symmetry of the Dirichlet-Neumann operator for Laplace's equation. We can write this in sort of in a flux formulation with approximate trace and flux, and apply HDG methods. And these results of myself and McLaughlin basically characterize multi-symplectic HDG methods and show that, in fact, most of the well-known HDG methods are multi-symplectic. All right, so as I mentioned, going through that very quickly, let me just briefly wrap up. So what I've shown is that geometric numerical integrators, which have really been developed over the last few decades, can preserve symplectic structure and momentum maps of Hamiltonian systems exactly. And backward error analysis shows that we nearly conserve a nearby Hamiltonian, preventing energy drift. Right? Sturm-Liouville is this standard workhorse method, which is explicit in order 2. And there are ways of getting higher order methods, either using Runge-Kutta methods or splitting methods with more stages. Second order time evolution PDEs often have this structure, and it's very natural to semi-discretize in space and then apply a geometric integrator in time. But to preserve this structure, you want to make sure that the semi-discretization doesn't break it. And this is particularly apparent when it comes to the gauge symmetry in Maxwell's equations and the preservation of the divergence constraints. And finally, hybrid and HDG methods are a useful tool for setting local conservativity of finite element methods, including this multi-symplectic conservation law. So, all right, thank you very much.
We have a burning question? David?
So on the sort of general question of, could we apply this to preserve the constraints in numerical relativity? I mean,
Yes.
So I'm a big fan of the, well, if you've got an idea for numerical relativity, why not try it out on the wave equation, Maxwell's equation first.
Yeah.
But for Maxwell's equations, you use a temporal gauge, and that we don't really use it, I think, very much an analog of that in numerical relativity. But we do use harmonic gauge, as sort of analog of Lorentz gauge.
Right.
So can you make your Maxwell's equation method work in Lorentz gauge as opposed to temporal gauge?
That's a good question. And I don't have a good answer. I know that there have been different ways of writing Maxwell's equations so Lorentz gauge is, this is different from Coulomb gauge, right? Or is it?
Right. It's basically give of A plus B5 and C.
Right. Okay. So I've seen people sort of take temporal gauge and then do the complete gauge fixing by setting div A equals 0. But I would have to look deeper into the literature. I don't know it well enough to know if people have done that. So.
I think that may have been done by John Victor a few years ago.
Oh, yeah?
Yeah.
Okay.
Yeah, with symplectic integration with, I think with Lorentz gauge, but I'm not absolutely sure.
Oh, okay. Yeah. I'd love to see a reference. Chat afterwards.
Anything else? Let me mention, we have a cancellation due to illness for the last talk tomorrow. We're going to replace it by something called second chances, which is a second chance to raise points. Once you've thought about it a little more, speakers can make points, but participants can raise their own points in discussion. So we'll have a discussion period tomorrow afternoon. So you'll have a second chance. Now you have a second chance about tea and coffee, and we're back here